Before you start repairing electronics, let's get clear on one important fact. As soon as the cover comes off, you are on your own, and you can get hurt if you are not careful. If you use proper precautions, you can learn to navigate all kinds of repairs safely. Let's look at a few ways you can get injured and how to avoid it, followed by the inverse, how you can damage the products you are trying to service. Electric shock is the most obvious hazard and easiest to happen. The insides of product are not designed for safety. You will find spots having dangerous voltages, and a slip of the tool can be serious. Even if the shock isn't serious, it will make you move your hands away and hit or cut it by the surroundings. Capacitors, especially the large electrolytics, can store a large amount of energy even after the power has been removed. Some can be fully charged even after many days. Usually, circuits will have discharge resistors for these capacitors, which will discharge them in a matter of minutes. But the only way to be sure if the capacitor is discharged is to discharge it yourself. Connect a resistor across the terminals to discharge the capacitor and keep it connected for a few seconds. And then remove and measure across the capacitor with your multimeter set to read DC voltages. It should read 0 or close to it. If not, apply the resistor again until it does. I combine the two methods by using the voltage reading measurement and attaching a resistor on the probes. In this way, you can discharge the capacitor while checking the voltage. These two are the terminals. So you can apply the resistor like this and simultaneously read the voltage present on it. This capacitor is discharged. The outsides of products are carefully designed to be user safe, but not the insides. It's easy to get sliced by component leads sticking up from the solder joints, or by the edges of metal shields or its chassis, and even by plastic parts, leading to cuts and bleeding. In this case, you can see these are the component leads which are sticking out. These are pretty sharp and can cut your finger if you are not careful. Now let's see some ways that you can damage your intended repair. Working with powered circuits is essential in many repair jobs. Sometimes when you want to probe a signal, you need the power to be applied to the circuit. You cannot probe signals when they are not present there. Probing around in devices with power applied presents a great opportunity to cause a short, sending voltages to the wrong places and blowing semiconductors. Many semiconductors cannot withstand over voltages or currents for more than fraction of a second. One of the easiest way to cause a short circuit is to press a probe against the solder pad, only to have it slip off the curved surface when you look at your test instrument and wind up touching two pads at the same time, essentially shorting them together. Anytime you stick a probe on the solder pad, be aware of this potential slip. Many times it causes no harm, but sometimes the results are disastrous. For example, if you are measuring across this pin and the probe slips and touches these two pins together, so you are essentially shorting them together. Electronic circuits fail in many ways. Let's look at some major types of failures that you will encounter. The first one is complete failures. Complete failures cause the piece of equipment to go totally dead. Equipment with some circuits still operating has not completely failed. Normally, this type of failure is the result of a major circuit path becoming open. Blown fuses, open power resistors, defective power supply rails, and bad regulator transistors in the power supply can cause a complete failure. Here we have a complete failure. We have a fuse blown open. Complete failures are often the easiest problems to repair. The next is intermittent fault. Intermittent fault are characterized by irregular circuit operation. The circuit works for a while and then quits working. It works one moment and doesn't work the next. Keeping the circuit in a failed condition can be quite difficult. Loose wires and components, poor soldering, and effects of temperature on sensitive components can all contribute to intermittent operation in an equipment. Intermittent faults are usually the most difficult to repair since troubleshooting can only be done when the equipment is malfunctioning. The next one is poor system performance. Equipment that is functioning below specified operational standards is said to have poor system performance characteristics. For example, if a power supply calls for 10 watts of power, but it is only outputting 5 watts of power, that is known as a poor system performance failure. Degradation of equipment takes place over a period of time due to deteriorating components and weakened power components. The next one is induced failures. Induced failures often come from equipment abuse. Unauthorized modifications have been performed on the equipment, or an inexperienced technician without supervision may have attempted repairs and damaged the equipment. Now let's take a look at the common causes of failure. The first one is over temperature or overheating. Except for components that are engineered for heat resistance, high ambient temperatures can have a destructive effect on various circuit components. In some devices, overheating can occur when a primary cooling system fails. Example are the failure of a heatsink or a cooling fan. The next is extended use. Electrical equipment that is extensively utilized beyond their specified lifetimes will eventually have failed components. The next is short circuits. Bridge terminals brought on by moisture, rusting, or broken down insulation can cause excessive current flow through electrical circuits, ultimately causing a short circuit. Short circuiting results in overheating, which can lead to electrical fires or explosions. This is an example of short circuit. The fuse has blown. The control IC has bursted open. The components are blackened. We also have an overheating effect right here. The transistor is burned. The resistors are burned. The next common cause of failure is overcurrent and overvoltage. As the name suggests, overcurrent occurs when the current flowing through a conductor is greater than its maximum rated current. Similarly, overvoltage occurs when the voltage within an electrical component exceeds its maximum rated voltage. Common causes of overvoltage are power surges, electrical arcs, and inadequate insulation. In situations where the supply voltage is far greater than the maximum operating voltages, the existing insulation even breaks down, leading some current to begin leaking through. Now let's take a look at the first steps to troubleshooting. Experienced technicians will have developed a method for troubleshooting. They follow certain logical steps when looking for a defect in a piece of equipment. As you gain experience in troubleshooting, you will start associating symptoms to a specific circuit function. A great place to start troubleshooting is by determining what is the most likely cause of the failure. The first step is to turn off power and discharge any capacitors in the circuit. Now the next most logical step is to check for fuses. Fuses help to isolate electrical equipment from power during abnormal conditions. An appliance that won't turn on may be due to the failure of a fuse. Multimeters can test for blown fuses by checking continuity between the terminals. If the fuse is of glass type, you can also see inside the fuse and check if it is working or not. Performing a detailed physical inspection of electrical equipment is vital to identify defects. Rust, cracks, chips, and other kinds of damage to internal components. Visual inspection also allows us to spot bridge terminals, loose wiring, broken down insulation, and blown components, which may result in open or short circuit and other failures. Passive components such as resistors, diodes, and capacitors control the behavior of electric circuits. Faulty or damaged components can cause several faults conditions. We can test and isolate failed passive components using a multimeter. Now another great tip is to divide the device into its functional areas. Electrical devices are composed of several functional areas such as power supply, processing, output, and so on. By testing functional areas separately, we can improve the accuracy of fault detection. Another method often used to troubleshoot electronics is to swap a good known component for the suspected bad component. Keep in mind that the good component could get damaged in the substitution process. Don't get into the habit of substituting parts if you are not sure if the component is faulty or not. This method works best when you have narrowed the failure down to a specific components. We will learn about testing each component. We will learn about testing each of the components individually in the upcoming lectures. Now let's take a look how to disassemble and assemble an appliance. You can get into nearly any product successfully and safely if you are careful and take your time. Disassembly is not a trivial process. Expect it to take a significant portion of the total repair time. Firstly, always disconnect power before taking something apart. This is true with battery operated products as well as AC powered ones. Even if there is no danger to you, you have a much higher chance of damaging the device if power is connected when things come apart, whether the unit is turned on or not. Now remove everything before you go for the screws, battery covers, rubbers, cover jack. If it comes off, take it off. And never force anything. If the case won't come apart or some corner seems stuck, there's a reason behind it. Perhaps some snaps are hiding on the inside of the plastic. Screws are sometimes hidden under labels and rubber feet. Run your fingernails over the labels, feeling for the indentation where a screw head might be lurking. If you find one, peel back the label just enough to get to the screw. Now let's take a look how to remove the outside screws. Firstly, start with the screws near corners and see if that frees up the case. As you unscrew anything, observe how it comes out. A normal screw should be rising above, indicating that it is screwed into a fixed object and it is not a nut. Sometimes there is a nut on the other side, like these recessed screws. These are holding components on the other side of the circuit. These will not help to take out this front cover. In this case, we can see the body is divided into two parts, the one outer shell and the base. We can see the lining right here, and same on the other side. So we can say by removing these four screws, the top cover will come off. Now, when the screws are recessed, they may not want to come out even if you unscrew them fully. Magnetizing a screwdriver helps with that. Let's take this case. We have four screws deep inside these holes. So a normal screwdriver won't be able to reach there. We will be needing a longer screwdriver like this one. Since you cannot see the screw, you have to feel. You have to feel and find the head of the screw. When you find it, you need to push it gently from the top and then you can unscrew it. Now the screw is loose, but when you want to remove it from the hole, you can use a simple magnet like this one, and when you attach it to the screwdriver, it becomes magnetized. So keep these screws safe. Now the next step is pulling wire connectors. Circuit board mounted connectors for wiring rarely have latches. If they do, the latch will be large and obvious, something you can squeeze with your thumb while pulling out the connector. Most wire connectors simply pull straight up. Grasp the wire, pull steadily without jerking, and the connector should pop out. Sometimes it helps to rock the wire left and right a little bit while pulling. And just like that, we have removed a connector. Also, we have connectors on the power supplies like these. These have a large latch which you can press when you want to pull them out. Now, after you have fixed the device, it's time to put everything back together. It's simple as to just screw the boards down, plug the connectors, close the lid, and you're done. But not performing the reassembly methodically can lead to all kinds of troubles, from failure of your repair to new damage, and even to danger to the product's user. Now let's look at the common errors that might be present while reassembling a device. The first most common error is replacing screw with another type of screw. If the screw is too long and it touches the circuit board, it can short a component on the circuit board, or it can touch the chassis and hence to the ground and once again short it. Over tightening screws can strip their heads, making it very hard to get them out again. Under tightening screws may lead to them falling out later. Now, manufacturers try to make internal connectors different enough from each other so only the correct type of connector will fit in. Like in this case, you can see we have two different types of connectors and both of them are different. And here we have the same kinds of connectors, but they are on a different colored wires. So it is hard to mess up. To begin reassembly, reverse the order in which you took the machine apart. When the unit has multiple boards, you will need to get the inner ones reinstalled first. Placement of wires and cables can be surprisingly important. When you took the unit apart, you might have noticed that some wires were tacked down with hot melt glue or silicone sealer. There's a reason for that. Maybe the wire needs to be kept away from a hot heat sink that could melt, or perhaps a cable carries a weak delicate signal that would receive interference if it got too close to some other elements of the machine. Or maybe the reverse is true. Sometimes wires carrying high voltages may be need to kept away from the other circuitry to avoid not only interference but also the possibility of arcing. So to begin reassembly, we can connect the connector back into its original place. Now perhaps the most important thing while reassembly is to check if any wire or cable is placed such that it will get crimped by a circuit board or part of the case when the reassembly is complete. In this case, when we are closing down the circuit, we need to make sure that none of the wires is being pinched by the circuit like this. The sharp ends of a board can go right through the wire's insulation, and it can cause disastrous results. Crimping caused by the case can break the wire or cut through the insulation and short it to the chassis. It is especially harmful if the chassis is made from metal. In this case, it is plastic, so it will not cause much damage. If the case was a metal case and this wire was a live wire which carried the live voltage, then the chassis will be live and the user can get a shock from touching the chassis. Sometimes the screw come from different spots where it will be harder to put back than they were to take out. Again, magnetizing the tip of your screwdriver with a magnet like this can help you place the screw in the right location. Always double check before closing that everything that came out from this device is back into the device. Like we have this battery retainer that we took out, but we forgot to place it back in. So these types of mistakes are pretty common. Now, if everything fits together well, you should be ready to fire up the unit and consider your repair complete. And don't forget to test everything. Be sure to bench test heat generating products if the work you did could possibly make them run too hot. It could have other problems like buttons that do not work because they are not lined up properly with the board. Test every button and every function.